Hi, I'm Zhang from Harvard University. Our paper is about attribute privacy, framework, and mechanisms. This is a joint work with Olga Ohrimenko, she's at University of Melbourne, and Rachel Cummings, she's at Columbia University. Attribute privacy protects the global properties of sensitive attributes in the dataset from leaking during analysis. For those of you who are familiar with differential privacy, we're used to thinking about privacy at the individual level, corresponding to rows of a database. And we ask questions of the form. What can an adversary learn about Alice data given the analysis of this dataset? In this work, we instead consider privacy of the attributes or columns of a dataset. That is, we take the view of a database owner who wishes to publish aggregate statistics about her database, and must also protect privacy of aggregate information in certain sensitive columns. In this example, the owner may wish to publish the average SAT score of its students, and let's assume that's non-sensitive information. But we know that the SAT scores are correlated with sensitive attributes such as race, gender, and parent income. So even though the SAT score is not sensitive, privacy protection is still needed to prevent leakage of these other attributes. Here are a few use cases for attribute privacy. Hospitals may want to share the number of COVID cases with federal health agencies, but want to protect their mortality rate, because then will affect their funding opportunities. And companies want to share their client data, but want to protect their own proprietary information. And researchers providing data for reproducibility in peer review process, but don't want other researchers to perform new analysis on the same dataset. In general, attribute privacy is to share aggregate statistics, but protect other aggregate properties that may be correlated with the shared information. Towards protecting attribute privacy, here several recent literature shows that global properties about the dataset can still be leaked even when we remove the sensitive attributes. And models with adversarial training, such as disentangled representation, has also been shown insufficient even to protect individual attribute privacy. And differential privacy can only be used to protect sensitive attributes at the individual level. So currently, the study of attribute privacy is limited, both in terms of a framework for reasoning about it and mechanisms for protecting it. First, I'm going to talk about the formal framework and definitions. Our formal definitions of attribute privacy are based on the pufferfish privacy framework. Pufferfish privacy generalizes differential privacy in two ways. It allows the analyst to specify distributional knowledge about where the data came from and the domain knowledge about what should be kept a secret. It can also accommodate correlated data, and the correlation was across rows. The pufferfish framework has three components: a set of secret S, then is a set of possible facts about the database we wish to hide, and a set of discriminative pairs Q, then are pairs of secrets we wish to be indistinguishable, and a class of data distribution theta that captures conservative assumptions about the underlying distribution, then generates the database. Formally, we say a mechanism is epsilon delta pufferfish private in a framework SQ theta. If for all possible data distributions, then in this class, and for all secret pairs with non-zero probabilities, and for all possible subsets of outcomes, the probability of the outcomes conditioned on the secret pairs should be close in this epsilon delta closeness notion, similar to differential privacy. We first introduce a data model for attribute privacy. A dataset X contains n records, each with m attributes. Each record is sample ID from an unknown distribution, where the distributions within a record may be correlated. And we let xi be the ith column of x, corresponding to the ith attribute, and xig is the ith attribute value of the jth record. C is the indices of sensitive attributes. And the goal is to evaluate a function f on the dataset x and release f of x while protecting some information about the sensitive attributes. We introduced two notions of attribute privacy. Before we make those definitions formal, I'll start by distinguishing them. The first one is dataset attribute privacy, which protects the attributes of a particular dataset, and the property of the attribute is modeled by a function g of a certain column. For example, the property could be, were there more Caucasians or Asians present in the dataset? Our second privacy notion is distributional attribute privacy, which protects the parameters of the underlying distribution from which the dataset was sampled. For example, the property could be, were there more Caucasians or Asians present in the population that was sampled to create this dataset? You may wonder, wait, aren't they the same? Well, they're almost the same in the above example, since GIX is an estimate of the phi I. But the distinction is important when guaranteeing privacy for unlikely realizations of the dataset, or when n is small and GRXI is a polar estimate of phi I. Here's our formal notion of dataset attribute privacy. For our data model that we talked about earlier, and for each attribute I, we let GIXI models the aggregate information about a particular sensitive attribute, and its codomain is UI. We formalize our attribute privacy definition using the pufferfish framework by specifying the three components, SQ theta. A secret is an event that GIXI takes value in a certain set, and S includes all secrets for all protected attributes. It could include all subsets for or only certain events. And the set of secret pairs Q includes all pairs of secrets on the same sensitive attribute. Theta is a set of possible distribution over X. In the pufferfish framework, it considers distribution over the entire dataset X, but we consider distribution over records. We resolve this by defining the theta to be the collection of distributions over a dataset, then induced by the allowable ID distributions over records. For distributional attribute privacy, it's a bit tricky. We let Xig is a data record sampled from unknown distribution. And this unknown distribution is described by a parameter vector phi. The main idea here is we define the secrets to be the attribute-specific random variable phi I, and this phi I is a marginal distribution of Xig conditioned on all other phi k fixed. Although it seems natural for phi I to define the marginal distribution of the ith attribute, this wouldn't capture the correlation across attributes that we wish to study. And instead, the phi I defines the conditional marginal distribution of the ith attribute given all other phi k fixed, which does capture such correlation. This also allows the distribution over datasets to be fully specified given phi and the size of the dataset n. And then our instantiation of the pufferfish framework is very similar to previous definition, with the attribute-specific random variable phi I taking the place of the attribute-specific function GIXI, and the theta is described by phi. Given the notion of attribute privacy, we also have three mechanisms to achieve that. Given the time, I'll only briefly introduce the attribute private Gaussian mechanism. We propose a variant of the differentially private Gaussian mechanism. It satisfies the epsilon delta dataset attribute privacy when f of x conditioned on the GI is Gaussian. We also relax this assumption and extend that to handle the non-Gaussian data in the paper. So for the DP Gaussian mechanism, it computes the true answer f of x and adds mean zero Gaussian noise with a variance that scales with the sensitivity of f. And the sensitivity is defined as the maximum change in the value of f caused by changing one row of the database. For attribute privacy, our Gaussian mechanism does the same, but now we need to have a new definition of the sensitivity. Here is our definition of sensitivity of f with respect to the ith attribute. This differs from the sensitivity notion used in DP in two key ways. First, we are concerned with measuring changes to the value of f caused by changing secrets rather than by changing an individual's data. And second, we assume our data are drawn from an unknown underlying distribution data. So f of x is a random variable. So our attribute privacy sensitivity bounds the maximum change in the posterior expected value of f in the worst case over all distribution data and pairs of secrets for each attribute. In the case that if f of x is independent of the protected attribute xi, then the sensitivity is just 0, and no additional noise is needed for privacy. Now we introduced our attribute private Gaussian mechanism. We also have a attribute private Markov proof mechanism that satisfies epsilon 0 distributional attribute privacy when attributes follow a Bayesian network. We also have an attribute private Warsaw stem mechanism that satisfies both attribute privacy definitions. The first two mechanisms are computationally efficient, but requires some assumptions. And the Warsaw stem mechanism is fully general, but is inefficient. So an open question is to design computationally efficient mechanisms without assumptions. As a conclusion, we introduce dataset attribute privacy and distributional attribute privacy to protect privacy of attributes rather than privacy of individuals. We show that pufferfish privacy framework can be instantiated to accommodate correlations across columns, which is needed for attribute privacy. We also provide three mechanisms for satisfying attribute privacy. As we mentioned at the beginning of this talk, attribute privacy has many applications. Future work includes applying and adapting these tools to relevant applications for domain experts. For more details, please check our paper online. Thank you.